Okay, folks, let's see if this is going to work. This is going to be the second time I recorded the lesson, but the first time it was just slightly too long. So I'm setting my stopwatch. We're going to get this thing done in under 15 minutes. This talk on topographic maps is simply to orient you. Ha! Little map joke. Okay, really little map joke. And it's also to wake you up. I know some of you are sleeping. Remember, you need to get about one chapter done every 8 school days to be successful. So wake up, get to work. If you've ever been out hiking, you might have seen one of these. A long time ago, when the United States was being, organized, the United States Geologic Survey, and previously known as the United States Coast and Geodetic Survey, went across the United States making sure what we had. And they would leave markers all over. These are called benchmarks. Don't mess with them, but they're really kind of cool. Here's an example of where a benchmark is. In this case, somebody walked up there, measured it, and it's 5,117 feet high. We're not doing that with survey instruments anymore. We're now doing it with satellites. But this is a typical topographic map. A little different from the ones you see on Google, but I'll show you the ones on Google Maps too. These lines represent the elevation. In this case, 4,400, 4,500, 4,600, 47, 48, 49, 5,000. This hill is just under 1 mile high, 5,280 feet being a mile. Here is a trail. This is the map you're used to. We've got names, we've got boundaries, we've got water, and that's about it. It's pretty generalized. This is a map I like. It's a geologic map of Arizona. Shows all kinds of regimes of different formations. This is an elevation map of a sort. It shows certain areas in Arizona are 9,000 to 12,000 feet high, and those are very few, by the way. Looks like just 3 points in Arizona. The Lucachuca and Chusca Mountains, the North Rim of the Grand Canyon, and Humphreys Peak or San Francisco Peaks in Flagstaff. And it also shows our lowest areas, way down here toward Yuma. This is a topographic map. These lines represent where the ocean would rise if it went up so many feet. How many feet? Well, let's take a look. This is 0 feet because it's the ocean. There's 100, and it takes 5 lines to go to every main contour line. These lines are called contour lines. Again, representing where the shoreline would be if the ocean rose to that level. There's a building, there's a road, there's a paved road. Let's count. 0, 1, 2, 3, 4, 5. 100 feet, it takes 5 lines to get here. So the contour interval, or what each line represents on this map, is 20 feet. So 100, 200, and it never gets up to 300 feet. If the ocean were to rise to 20 feet, no, let's say if the ocean were to rise to 100 feet, it would go somewhere across here, way up this valley, and we can't tell after about this point. And at 100 feet, it would come back down. There's the 100-foot line. So it would come back down somewhere along this cliff and then off this direction. Let's start more simply. This is Sea Island. This is an outline of the island. If the ocean rose 20 feet, this would be the new outline of the island. B and D are both at 20 feet. C and A are both at 0 feet. If we continue to draw new shorelines, raising the ocean 20 feet every time, this is what the ocean would look like. And this is kind of cool. You can tell that this side of the island is more gently sloped, and this side of the island is more steeply sloped because the contour lines are closer together on the northeast side than they are on the southwest side. By the way, it tells you the contour interval on here, and here's a cool scale. People a lot of times will think this thing is 2 miles long because it says 2 miles long. It's not. It is 3 miles long because 0 is in the middle. Be careful if you use a scale like this to measure distance. Here's another example of contour lines, and notice that contour lines bend upstream when they cross a valley. It's because the valley is incised or depressed in the land. Typically in class we do what's called a profile. We're not going to do it here, but it's good to know. If this is a hill on a map and you lay a piece of paper right next to this and cross on the piece of paper the elevation lines wherever your paper abuts them, like right 0, 20 feet, 40 feet, 60 feet, 80 feet, 80 feet, 60, 40, 20, 0. And then you bring those down to graph paper and you put those dots on here. Notice 0, 20, 40, 60. So you put your 0-foot line right here, 20, 40, 60, 80, 80, 60, 40, 20, 0. You can get a profile of the mountain. This is pretty cool. People in Hollywood do this all the time with CGI type things. However, this is a real exaggeration. About 1 inch here is equaling 80 feet. 1 inch typically on a topographic map will represent a mile or a half mile. So this is way vertically exaggerated. Remember the island we had before? It was pretty simple. This island has a crater in it. How do you mark a crater? Well, everybody except for Google Maps creates what's called a Hatcher line. In this case, it indicates a depression. Just looking at this makes me sad. Oh, sorry. Here is a really cool little map. Almost everything you need to know is on here. Moose River is heading from northwest to southeast. Contour line, or the contour interval, is 20 feet. This line is about 3 miles long. Let's see if we can do something here. What's the elevation of Z? This is 1,000 feet, so that has to be 1,020. What is E? It's got to be 1,040, so is Y. That makes sense because there's a benchmark here at 1,045. So this has to be a little bit higher than 1,040. Here's the 1,100 foot line. They didn't mark 1,100 on every one. Here is a spot elevation. They didn't leave a benchmark here, no brass marker, but they've measured it. There could be a little monument there. This is a mining monument, by the way. And this hill is 1,109 feet high, just slightly higher than 1,100 feet. If it were 1,120 feet, there would have been another line here. By the way, if this is 1,000 feet, the first line that's a hatcher is also 1,000 feet. That means this is 980 feet. So this has to be below 980, but not as low as 960 because there's no other line. Where contour lines again are close together, it's very steep, and where they're far apart, it's probably a little safer skateboarding. Although, yes, I know some of you would skateboard off that. Here's the map you're used to. In the computer age, this is what we look at most often. If you ever go to Google Maps, scroll down to terrain. And this is what happens. It gives you an artist type thing showing you the terrain of the land. Now this is a lot more handy than this, I think, if you're going out hiking or exploring, or if you're interested in geology. In particular, we're going to go up here to the west of Winslow, the most important town in Arizona, where I was born. And look at that little mark. Why? There's that mark again. Some of you know what this is. Some of you may have been there. There it is again. There's the creek. And here we go. Here are the contour lines. In this case, what's the contour interval? 5,200, 5,400. It takes 5 lines to go. So 5 lines to get 200 feet. That means 40 feet per contour line. The contour interval is 40 feet. 5,600 feet here, 5,600 feet here. This line is the same line as that. It's just that this hill has gone up to a rim and then back down. This is Meteor Crater. This is like shooting a BB into a window. You may have seen something like this. Or in my case, I shot a BB into the roof of my dad's truck and left a big hole that looked something like this. Oh well. We're going to look at this hill and this hill. This is just to the northeast of Flagstaff. Again, let's look at this one first and then we'll go to that one. Oops, backwards. Google, again, doesn't make hatcher lines indicating depressions, but you get the idea. Here's 5,800, 6,000. We're well above a mile in elevation here. That has to be 6,200. It goes up to 6,240, and then it goes back down to 6,240, and then 6,200. And then it drops back down inside this crater. Notice out here the contour lines are far apart because away from the craters, it really is fairly flat. Here's another type crater, but it's been eroded away. There would almost be a stream in here if this weren't made out of cinders and the water soaked in. This is Humphreys Peak, or what you know as the San Francisco Peaks. It was a huge volcanic field. This part has blown away, I believe about 600,000 years ago. I used to wake up being scared that this would erupt again. Silly me. If you ski in this area here, the snow bowl. You right up here. You don't go all the way to the top, but somewhere right about here, and you run back down. Very few people ski in the inner basin here, but it is kind of cool. This is one of the few places in Arizona where we've had glacial action. This is the southwest corner of Catalina Island, and you can see what would happen if the ocean rose 200 feet, 400 feet, 600. Here's the interior of the Grand Canyon. You're welcome to pause this at any time. I just have to finish this video in 15 minutes. Here are some symbols for maps. Let's look at this at the very end of the lecture. This is important. When you're organizing a state and you want to start selling off your land or measuring land, knowing what you have to have a place from which to measure. You have to have a line that, let's call it your home plate or your base. In fact, in Arizona, we call it the baseline. And there's a road named Baseline Road because everything in Arizona is measured from this mark, which is right at the end of Baseline Road. By the way, this is also PIR, Phoenix International Raceway. Baseline Road is somewhere right down here, and everything is measured north or south of that. Here's an engineer on a rainy day showing you everything is measured from there. Something else that's important. Magnetic north and Earth north and North Star are not all the same. If you put a compass on a map, it's going to point this direction. True north is that direction. Why? Here we are in Arizona. True north goes this direction. Your compass is going to point to Elif Island because it is under that the North Pole of the United States, the world, exists. Your compasses are drawn to that by the magnetic pole. By the way, every once in a while, Google Maps makes a mistake. Here, for some reason, they just cut off the edge of the island and put water at 200 feet. This can't exist. It's weird. This is a little place where I used to live called Pongo Pongo. And yes, it really is pronounced that way. Here's another weird goof up. Let's go back to this. This is a nice key to lots of the symbols that you find on a topographic map. Here are benchmarks, things that have been measured. Topographic lines are brown. Every fifth one is a darker brown with the elevation. Everybody but Google uses depression contours. Here are boundary marks, usually in black. Things in water tend to be blue. Vegetation tends to be green. Mangrove swamps you probably won't see in Arizona. Mines have their own symbols. This is for hard rock mine. This is for sand and gravel. Here are other places that we've messed up. Here's a levee. You'll study that in the River on chapters, and you won't see that in Arizona. Here are township and range lines, how we mark off 6 square mile areas in Arizona from baseline. You're not going to see a lot of this blue in Arizona because these are ocean features. And here are rivers and lakes. Lakes tend to be in blue. Dry lakes, we have a lot of these in Arizona, tend to be blue lines with brown dots. Sandy washes are like this. And most of our rivers are what we call intermittent rivers or streams. They'll have dots in them because they're not permanent. Folks, I think I just did it. We got it in 13 minutes. I hope this was helpful. Bye-bye.